Let's see the steps for the revised simplex method. So, step one, you just express the given problem in a standard form. So, you just write it in a standard form. That is, we just make your objective function as one of the constraint, and we can make this there's adding a slack variable and make this inequality to the equality, and then we just make this table. That is, you just obtain a basic feasible solution, IBFS. So for IBFS, we can have, that is, after making this IBFS, we just consider the linearly independent column vectors, and then we can write on your basis vectors, and considering the naming, or consider the basis inverse B1 inverse as beta naught. This beta naught of 1 is nothing but the first iteration of the identity element, and beta 1 is the second column, and beta 2 is the third column of your B1 inverse, and B2, B3 in B3, beta 3, beta 4, and so on, beta M. So, like that, we are having the B1 inverse, that is the columns which are making linearly independent column vectors. That is, the columns or the vectors which are making the identity matrix. So, these vectors are nothing but the basis vectors, and this matrix is nothing but the basic matrix, and this B is nothing but the solution, that is xb, and basic variable b, and we have included the objective function as one of the constraints. So the first row should be the coefficients for the objective function. So the z is also a basic variable, so z, and the solution for z is 0, and the column vector, it should be 1, and the remaining coefficients are 0. So we can fill this iteration, and you can leave your yk as such, because we want to find it out yk using ck minus zk. So we just want to find it out the corresponding k. So with that corresponding k, you can find it out your yk. With that yk, we can use your minimum ratio. We just find it out the leaving vector. So for finding out your Cj minus Zj, that is, if all the Cj minus Zj is less than 0, the current basic solution is optimal. Otherwise, we just want to go to step 4. That is, we just want to select a variable which is entered to the basis, that is key column. So for key column, we just want to find it out this Cj minus Zj. So for finding out the Cj minus Zj, we don't want to find it out all the multiplications and summations and all. So instead of that, we just use the first row of your B1 inverse into the columns which are not in the basis. So that is B1 inverse into AJI. So that is nothing but, instead of that, we can find it out your max of Cj minus Hj, where all the Cj minus Hj should be greater than 0. So we just want to select a variable to enter into the basis. For each non-basic variable, we just want to calculate Cj minus Zj. And this all Cj minus Zj is less than 0, then the current basic solution is optimal. The net evaluation is optimal. Otherwise, we have to go to step 4. If not, we just want to go to step 4. So what is your step 4? We just want to find it out the basic variable, that is which the basis which should be leave, that is we want to find it out the key row. So for that, we just calculate your yk is b1 inverse into ak's are nothing but the columns which are not in the basis. So we just want to find it out your yk, and after calculating your yk, we just have your minimum ratio, that is xb by yk, and all your yk, the condition for yk should be greater than 0. If it is less than 0, so we should not take it. That is, if all the yks are less than 0, then the solution is feasible, infeasible, right? So the vector beta is selected to leave the basis, and if the minimum ratio is not unique, the ratio is same for more than one row, then resulting basic feasible solution will be degenerate. So to avoid this, we just use the usual method for degeneracy. Okay, and we want to update after finding out the inserting and leaving. We just find out we need to update the current solution. So for updating the current solution, how we can do it? Update the initial table by introducing the non-basic variable into the basic variable. That is removing the basic and introducing the non-basic, which should be basic. So while if we want to make it to a basic, it should have the linearly independent column vector. So that's why we just repeat your step 3. So using that, we can find it out the improved solution. So likewise, so these are the steps to find out or to find the solution of the LP problem using revised simplex method. So in the next video, we'll see about or we'll explain the let me explain one example problem solving or using the revised simplex method for solving linear programming problem. Thank you.